Hello and welcome to the second part of this, which is our 21st lecture of our course on photonic devices. If you recall, on the first part of this lecture we talked about the responsivity and the quantum efficiency of photodiodes, and on this part of the lecture we're going to discuss the response time, which is another key parameter in photodiodes, because it's going to determine the maximum operating frequency of the device, right? And basically the response time depends on two quantities, right, or two parameters. The first one being the transit time associated with carriers, electrons and holes, subjected to an external electric field. So this means that it takes a certain amount of time for an electron or a hole to cross the depletion region or the active region of the device, and this speed with which these carriers move inside the depletion region determines the speed and the maximum frequency of the device, right? The other parameter is the RC time constant of the photodiode inside the detection circuit, right? So usually the typical devices that we'll discuss are formed by reversed bias PN junctions or PIN junctions, and these as opposed to the optical sources, the LEDs and the laser diodes, which were forward bias junctions, right? Here we have reverse bias junctions, and this means that the junction itself is going to have a considerable capacitance associated with the space charge in the junction, right? The immobile ions in the P and N side of the junction, as we've said before, are going to have a capacitance because they will behave as if it were a parallel plate capacitor, basically, and therefore there is a capacitance associated with the device. And on our next lecture we're going to discuss the polarization circuits, but basically the way that the device is polarized is by placing it inside a circuit which has a load resistance, and sometimes, the voltage across this resistance has to be amplified by an op amp or some sort of or other types of amplifiers, which will also have an input resistance. So the capacitor is going to be in the context of a circuit. So the diode, the photodiode, is going to be inside a circuit which has a certain equivalent resistance. So therefore you'll have basically a series RC circuit which is going to have a RC time constant. So the maximum speed with which the voltage of this across the load of this circuit can respond depends on this RC time constant, as we would expect. So these are the two parameters that are important when talking about the response time, right? So the transit time of the electrons and holes and the RC time constant of the circuit. Now, the reverse bias polarization implies that there's an electric field inside the depletion region, right? So if we're talking about a typical PN junction, just to make things a little bit easier, we have a PN, the PN semiconductors and the immobile ions, which, let's recall, that should be negative on the P-type semiconductor and positive on the N-type semiconductor inside the depletion region. And if we reverse bias this device, we'll have an additional voltage applied across the PN junction in this direction, which which produces an electric field in the same direction as the electric field generated by the immobile ions in the depletion region. So the point is that there will be an electric field inside the depletion region, an electric field E, and the drift velocity, or the speed with which the electrons and holes will move inside this region, right, in order to contribute to the current, is going to depend on the mobility of the respective carrier. So have carrier mobilities for electrons and holes which are different in different materials, as we know. And the drift velocity is just the mobility multiplied by the electric field, right? This is a classic expression for the drift velocity. And the carrier mobility is given in units of centimeters squared per volts per second, and is different for electrons and holes, right? But the point is that depending on the electric field intensity, which is going to depend on the polarization and the mobility of the carriers, they will have a different drift velocity. So now we're actually talking about the device, and we're focusing on PN junctions or PIN junctions, but usually in these devices the region which will be used to detect light, in other words the region where the light will be absorbed, is the active region or the depletion region. This will be the region of importance here again, right? So the impinging photons will be absorbed in this region, and this region will have a certain width. Now what we're calling the width is this dimension here, right, perpendicular to the interface, to the junction. So the depletion region of the reverse bias diode has a length W, which will be larger than the length of the depletion region of a forward bias diode, as we know. So the transit time that it takes for electrons and holes to get across the depletion region is going to depend on the drift velocity, right? So we can write that the drift velocity, so if velocity is distance over time, right, we can write that the drift velocity is related to the transit time, which we're calling tau d, right? And the transit time here is just the time that it takes for an electron or a hole to cross, right, from right to left in the case of a hole, and from left to right in the case of an electron. But the time it takes for these carriers to get across from one side from one extreme to the other of the depletion region, right? This is the transit time tau d. And if Vd is the drift velocity, is the velocity of electrons and holes, right? It's going to be different for electrons and for holes, but if Vd is the drift velocity and W is the length of the depletion region, therefore tau d and Vd are going to be related by this equation right here, right? Vd is equal to W divided by tau d. And if we isolate tau d, then we see that tau d, right, the transit time is just W divided by the drift velocity. So what we want is large mobilities and large drift velocities. And again, this is a parameter which depends on the device, right, the mobility of electrons and holes, which depends on the material, right? The mobility of electrons and holes depends on the material. But usually we want a large drift velocity in order to have small transit times, right? So that in such a way that the electrons and holes can transit across the active region in a time that is small enough so that the device can respond fast, right? Basically can operate at high frequencies. So if a pulse shorter with duration, right, shorter than tau d, so let's consider that the detector is detecting light pulsed beam, right? So optical pulses, and if a pulse, an optical pulse, has a time duration that is shorter than tau d, and it impinges on the detector, it will not respond fast enough as we expect, right? Because by the time that the pulse ends, the generated carriers will not have been able to get across the depletion region fast enough. So the device, as we would expect, is not going to be able to respond fast enough, right? So therefore, carrier mobility, which depends on the material, and the length of the device influence the response time, right? In order to have small transit times, which is what we would desire for a fast device, we need to have small depletion regions. So a small w, the length of the depletion region would have to be small, and the drift velocity, which is equal to the mobility multiplied by the electric field, would need to be high. So we ideally would desire to have large carrier mobilities inside the material. Okay. Now the other parameter that we've mentioned is the RC time constant of the photodiode in the detection circuit is given by tau RC equal to the total resistance seen by the diode, right, multiplied by the junction capacitance, right? So therefore, in this expression, RT is the total resistance, which often is the load resistance, an actual resistor that you place in the polarization circuit in order to convert the photocurrent into a voltage. And in parallel to this, typically you would have the input resistance or the input impedance of the amplifier, which is used to amplify the voltage which is generated across the load resistor, right? We'll take a look at these polarization circuits in a little more detail on our next class, but basically this is the total resistance or the equivalent resistance seen by the diode in the polarization circuit. The junction capacitance, as we would expect, similar to the capacitance of a parallel plate capacitor, is going to be equal to the electrical permittivity of the semiconductor, right? So epsilon S here is the permittivity of the semiconductor multiplied by the area divided by the length of the depletion region, right? And here again we can take a look at what the junction looks like to get a better grasp of why this expression is the way it is. But if you have a PN junction here, for example, you have immobile ions on either side of the junction, and as we've said, these immobile ions or this depletion region will behave in a similar manner as a parallel plate capacitor, because you have, although they are, they have a spatial distribution here, you have a positive charge on one side and negative charge on another side, just as you would have if you applied a voltage across a capacitor. Now the semiconductor has a permittivity which is epsilon S. For the parallel plate capacitor, you would multiply epsilon S by the cross-sectional area, so the area of the plates here, right? So let's try to depict this a little bit better. So A is the area of the plates, and similarly here A will be the area of the device, along this perpendicular direction here, right? So therefore A will be the cross-sectional area which I'm hatching right here, right? And the length W is the length of the depletion region, right? So basically the junction capacitance is just this. And in order to have a small time constant, which is what we want, if we want the device to operate fast enough, at high frequencies, then we want both a small total resistance and a small junction capacitance. And note that in order to get a small junction capacitance, what we want is a small cross-sectional area and a large length of the depletion region, right? A large W. Okay, so the cutoff frequency of the detection circuit is going to be given by this equation right here, right? It's going to be given by 1 over 2 pi times tau RC, which is equal to R total times the junction capacitance. And in order to have fast detectors which operate up to large cutoff frequencies, we need small capacitance and small total resistance, right? The load resistance in parallel with the input resistance of the amplifier and so on needs to be small, so ideally it should be small, and the junction capacitance should be small as well, which means a small area and a large length. Note that the length of the depletion region, or this W parameter here, influences both the RC time constant. So here we ideally would want a large depletion region length, but it also has an influence on the transit time, right? So from this equation here, we see that the transit time goes up with the depletion region length. So ideally here we would need a small depletion region length, right? Sometimes referred to as the width of the depletion region, but in other case the dimension that we've pointed out here, right? This dimension right here. So in order to decrease the transit time, we would ideally want to decrease this, but in order to have a small junction capacitance, we actually need to increase this. So sometimes, there needs to be a compromise in order to find an optimal value for this, right? But basically the takeaways here are that the response time depends on the load, the load resistance connected to the diode, and also another important point is that in most detectors the transit time is minimized, right? So the length of the depletion region is small enough that the transit time is not a big issue, right? And the RC time constant is actually going to be, in most cases, the parameter that determines the bandwidth of the detector. So the limiting factor here usually is the RC time constant rather than the transit time. But this is, for most photodiodes in any case, right? Okay guys, so this was it for this, which was our first lecture regarding photodiodes. On our next lecture we're gonna finish up this topic by discussing some typical kinds of photodiodes used in optical detectors for optical communications, as well as some of the most commonly used polarization circuits, right, which are used in order to reverse bias the diode used to detect light. Okay, so thanks a lot for sticking around, and I'll see you on our next lecture.